Welcome to the table creation lesson, where we explore the most fundamental aspect of any relational database, which is how to create tables. We'll start with basic table creation, then cover temporary tables, what their benefits are and how they can be used, so that you can jump on column definitions, where we'll practice what we learned in data types lesson, as well as generated columns. Then we'll finish with basic constraints, what they are and how they contribute to data quality through data integrity. So let's jump right into it. Let's start with the basic create table syntax. In PostgreSQL, creating a table involves specifying both its structure and behavior. Here is our first example. Create table customers. Within parentheses, we define the columns. Customer ID is an integer, first name is a varchar of 50, last name varchar of 50, and email varchar 100. So now let's break down each component of this statement. The create table keywords tell PostgreSQL we want to create a new table, followed by the table name in the list of column definitions within parentheses. The first column, customer ID, is an integer. Remember that from data types lesson? So it's reserved 4 signed bytes to store whole numbers from around negative to positive 2 billions. The next 3 columns, first name, last name, and email, are all character varied, with maximum capacity established by 50 characters for name fields and 100 characters for the email. Linking to our last lesson, we can explicitly specify the schema when creating tables. In the same command, just type the schema name and a dot before the table name. It's simple as that. So if you remember well our discussion about the schemas in the last lesson, what schema was our customers table created in? Most likely public, as our search path should be the username, and we probably haven't created a schema called Postgres, followed by public, which is always created. Temporary tables in PostgreSQL are session-specific tables that exist only for the duration of a session or transaction. They are particularly useful for complex calculations, staging data, or breaking down complicated queries into manageable steps. Here is the basic syntax for creating a temporary table. You set create, then the temporary keyword followed by table and the table name. Again, we surround all table columns with the round brackets. This time, our temp orders table contains another ID attribute of type integer, or int4, if you remember well, in a total amount of type decimal. A fixed precision numeric field with 12 decimal digits, reserving 10 of them to the whole number and 2 of them to the precision side. At the end of the instruction, we define onCommit drop. So let's take a look at onCommit options. After closing the parentheses, there is a special command clause onCommit that is used to define an automatic behavior once transactions in the current session are done. So PostgreSQL provides 3 onCommit behaviors for the temporary tables. The first and shortest one is onCommit drop, which automatically drops the whole table at the end of the transaction, so it will be no longer available after that, and you are forced to recreate it if you still need it. The second one is onCommit delete rows, which keeps the table structure but removes all rows at the transaction end. So it's kind of a table that might be populated during the transaction and will automatically be flushed out or truncated after that. The last option is onCommit preserve rows, which maintains both structure and data until the session ends, when the temporary table will be dropped no matter what onCommit option you choose. Think of these options as different levels of persistence. From completely temporary is the drop, to lasting throughout your session, which is preserve rows. Here's a practical example showing how temporary tables can simplify complex operations. The command starts with create temporary table, and the table is daily sales, to temporarily store summaries from today's sales. Here we are planning to reserve 1 record per product, but aggregate all sales in the current day for each record, so that we have a total quantity of units sold in that particular day, as well as the revenue. The reasoning for the onCommit preserve rows is a data analyst behind this session wants to keep the summaries between different transactions, so they don't need to query again. Imagine a huge number of sales per day, so the query to populate this table takes very long to process. On the other hand, there is no reason for this table to exist after the session is done, as no one else will be maintaining it, and it might become stale very quickly. In other words, it's a table just to help with some specific one-off analysis. After creating the table, there is a command based on the combination of 2 commands that we are going to cover in future lessons that will populate it. So I'm not going to spend too much time on it now, but I'm pretty sure you can guess what it does just by reading it. And that's the beauty of declarative language like SQL. The command says insert into daily sales, our temporary table, whatever comes from select of product ID, the summatory of quantity and summatory of quantity multiplied by unit prices. And that's exactly the calculation for single revenue. The order of fields in this select is important as they follow the creation order of the fields in our previous create table command. Continuing with the select command, the data source is an existing table orders, and the query filters records by just the ones whose register order date is the value in the system variable current date. You will learn in a following lesson that sum is an aggregate function, which means it swallows all records available, or in this case filtered by the where clause, and squash them into just one, unless you provide a group by clause. And that's exactly what we did. When we provide group by product ID, we say, hey, give me one record of all orders per product ID that were sold today, along with the sum of quantities, which configures the total quantity in that day, and the sum of quantities times unit prices, which configures the total revenue from that product in the current date. Once populated, daily sales can be used for any purpose, like selecting all records whose revenue is greater than 1K and so on. If you have already seen aggregate functions, group by, and also another clause called having, you should know that this example alone isn't better than just a single query with all of these features I just mentioned. However, what I want you to focus is the idea of having a temporary storage for something relatively expensive to compute, so that it can be reused multiple times during the session, while the current user sessions lasts. So the key benefits of temporary tables are improved query performance by storing intermediate results, simplified complex multi-step operations, reduced network traffic for client applications, automatic cleanup when the session ends. Of course, one common use case is breaking down complex analytical queries into smaller, more manageable steps, like we just done. We can also point out some best practices when working with temporary tables. Use meaningful naming conventions. Random examples are temp underscore prefix or underscore TMP suffix, just to differentiate temporary from regular tables. Choose appropriate on-commit behavior based on your needs. You can always drop temporary tables explicitly as soon as they are no longer needed, so you don't have to wait until the session ends. Be careful with session memory usage with large temporary tables. Each call in PostgreSQL requires two basic elements, a name and a data type. Let's explore best practices for both. Regarding naming conventions, choose descriptive names. Be consistent across your database. Use lowercase names separated with underscores, a naming convention called snake case. There are many reasons why this convention is the most popular among database object names. But of course, you're free not to follow them. In this case, just fall back to the convention number 2 and be consistent. Look at this example. Create table products with product underscore ID, name, price, created underscore at, and is underscore active. Some data types allow or even require additional parameters to control their behavior. Like what we learned in data types lesson, limited character types like char require or allow the size limit, while text is always unlimited, so no extra parameter is allowed. For numbers, you can control size and precision. Time-related types include time zone options. In this case, the syntax does not use round brackets. These parameters help optimize the storage and ensure data accuracy for your specific needs. PostgreSQL allows you to define columns whose values are automatically calculated from columns in the same row. These are called generated columns, and we use them with the syntax generated always as or generated by default as. Generated columns are useful for storing calculated values that you frequently query, enforcing business rules at the database level, and simplifying queries by pre-calculating common expressions. There are two types of generated columns, stored and virtual. Stored generated columns are written like in this example, where price with tax is generated always as. Then within round brackets, you define your formula. In this case, price times 1 plus tax rate, which is the column defined above. Finally, the store keyword indicates that the value is calculated when the row is written and physically stored in the table. Up to version 17, PostgreSQL does not support virtual. despite both types being conceptually defined in the documentation. While store-generated columns are computed when the data is written, inserted, or updated, and physically occupy storage space, virtual-generated columns would be computed on the fly when read. It wouldn't take up storage space. The good news is that PostgreSQL 18 expected in 2025 will introduce virtual-generated columns. With this upcoming feature, the virtual keyword will become actually useful, and in fact, virtual will become the default if neither store nor virtual is specified. The addition of virtual-generated columns will provide developers with more flexibility, using store columns when write performance is prioritized, and virtual columns when the storage space is a concern or when the data is infrequently accessed. It's important to know some rules of generated columns. You cannot directly insert or update values in a generated column. The generation expression can only reference columns in the same table. The expression cannot reference other generated columns. Constraints are rules that enforce data integrity in your database. PostgreSQL provides several types of constraints that can be applied at both column and table levels. Column-level constraints are specified as part of the column definition. It's usually the easiest way to define constraints that do not span across multiple columns. This simple example shows a unique constraint on product code, which means there can only be one product code per record in products table. Name has the constraint not null, which makes this attribute mandatory. Price has a check constraint complemented by a logic within round brackets, so prices cannot be negative. Finally, status defaults to A, which means when a new record is inserted, if no status is provided, the letter A will be used, A for active, for example. Table-level constraints, on the other hand, can involve multiple columns and are specified separately from the column definitions. This new table has two constraints declared underneath the list of columns, but still within the table's declaration parentheses. The first constraint is also a check, with similar logic of previous product price. In this case, the inventory quantity cannot be negative. That will mean over-demanded products from a particular warehouse. The unique constraint this time is different as it comprises two columns. This tells us that inventory records can repeat the product ID as long as they are linked to different warehouses, and vice versa. Warehouses can also be repeated across multiple products within the same warehouse. What cannot be repeated is the same product in the same warehouse, as this table is used to tell us how many items of a specific product there are in a specific warehouse, and when was it physically inspected to make sure the quantity is correct. Let's list all the basic constraints. Not null. These constraints ensures a column cannot contain null, which is the absence of values. Unique ensures all values in a column or group of columns are distinct, as they can never repeat. You can conclude that for all new insertions and updates of unique columns, the database needs to perform a search for an existing record with the same value. To overcome performance bottlenecks, PostgreSQL creates indexes for unique columns, which can significantly reduce the time spent on these searches. We'll dissect indexes in session 6, Performance and Optimization. Check ensures values in a column or group of columns meet certain conditions. Finally, default specifies a default value for a column, or a value when nothing is explicitly provided. Let's go through more practical examples to examine constraints one by one. Not nulls are column-level constraints that ensures required data is always provided. In this example, all orders have explicitly provided values on order date and shipping address columns, while notes can contain nulls. Unique constraints can be applied to single columns or group of columns. Because of that, unique is allowed on its own constraint declaration. Basically, a constraint declaration is useful when you need to go across multiple attributes, and you also benefit from giving it a name that makes sense to your use cases. In this example, employees have unique emails and phone numbers, which makes total sense, but country code and national ID can individually repeat, but not the combination of the two. Check constraints can also be applied to single columns or to the whole table as they enforce domain integrity by specifying logics for valid values, like ranges or patterns. It's when you are free to provide a logic according to your business needs. For example, valid price is a check constraint that restricts prices from being 0 or lower. Valid discount checks and only allows discount prices lower or equal to price, which is a great example of a check that uses two columns. Valid status accepts only A for active, I for temporary inactive, or D for discontinued products. Default constraints are super straightforward and provide automatic values when none are specified. Audit logs event dates are automatically assigned the current timestamp, now, and by default are not processed, assuming that any system will check logs from this table and perform any action that we understand as processing the log, so it might change the process flag to true later. When you define a column with a default value in PostgreSQL, the database handles this differently depending on whether the default is volatile or non-volatile. A non-volatile default is a constant expression that doesn't change between evaluations, like for example, default active, default 100, or default true. A volatile default, on the other hand, can return different values each time it's evaluated, such as default current timestamp, which obviously takes the current timestamp every time it's called, default random, or default UUID generated v4 for UID identifiers. For non-volatile defaults, PostgreSQL optimizes storage by keeping the default value in the system catalogs, rather than writing to every row. When you query a table, rows that haven't had an explicit value set for that column will have the default value returned on the fly from the system catalogs. This optimization saves significant storage space, especially for tables with many rows. Volatile defaults, however, must be evaluated and stored for each row at insertion time, as their values depend on when they're executed. While PostgreSQL automatically generates constraint names, it's best practice to name them explicitly for easier maintenance. So when you do, remember to use the scripting prefix like chk for check or uq for unique, and so on. Remember to be consistent with that. Include table and column names, especially when dealing with one single column in your constraint. Finally, keep names concise but meaningful. And that's all for this lesson. Here we just learned how to create tables, also called relations, which are the most fundamental structure in a relational database. You also had a glimpse over temporary tables and situations where they become handy. You delve into column definitions, leveraging your data type knowledge built in a previous lesson. Then you finish with basic column level and table level constraints, what they are and how to create them. See you in the next lesson.